Hey guys, welcome back. So last time we talked about properties that parallelograms have. They have quite a few. And so today we're just going to expand on that. We're essentially doing all of those things in reverse, which is now proving. So we're back to writing some proofs. Proving that a quadrilateral is a parallelogram. So these are all properties that we talked about the other day. And I'm going to try to show you the theorems and give you kind of a quick proof so you can see how they work if they don't kind of jump out as obvious to you. So first thing we talked about, one of the properties the other day was that a parallelogram by definition has opposite sides that are parallel. So if you're given that, then it is a parallelogram by definition. Now another property that they have is that the opposite sides are congruent. So now we can do this in reverse because it so happens that if the opposite sides are congruent, it is going to be a parallelogram. So if a quadrilateral has two pairs of opposite sides congruent, then it is a parallelogram. Okay. So the proof for this is pretty straightforward. You need to kind of create a diagonal for yourself. So I'm just going to draw in the diagonal AC. Okay. And so clearly AC is congruent to itself by the reflexive property. So if you draw in that diagonal, you can see here that triangle ABC is congruent to triangle CAD. Okay? Oh wait, ABC, excuse me, CDA. Alright, be careful with the naming there. And so I'm going to just kind of run through this. I'm not going to write a two-column proof here. I'm just going to try to write down the steps just so you can see where it comes from. So I'm just going to number those angles just for simplicity here, so I don't have to write out all of the letters. So these angles here, angle 1 and angle 2, are congruent by CBCDC. Okay, so they are corresponding parts in congruent triangles. Therefore, they are congruent. And because they are congruent, they actually are alternate interior angle pairs for this transversal AC and the sides or the lines BC and AD. So by the converse of the alternate interior angle theorem, we can see that AD is parallel to, excuse me, AD is parallel to BC. By the converse of the alternate interior angle theorem. Okay. Second theorem here, one of the other properties we have is that in a parallelogram, the opposite angles are congruent. Okay. And so the converse of that will actually prove that it is a parallelogram. So if a quadrilateral has two pairs of opposite congruent angles, then it is a parallelogram. All right. So for the proof of this one, what I'm going to do is I'm going to pick two variable measurements for these angles. So I'm going to call this double-sided mark here. There's two tick mark angle X degrees, and the single one I'm going to call it Y degrees. All right. And in the first day of this chapter, we talked about the sum of the interior angles of any polygon. This being a quadrilateral, the sum of the interior angles here is 360 degrees. So 2x plus 2y adds up to a total of 360 degrees because this is a quadrilateral. And what we can do is we can actually kind of simplify this, or we can reduce everything by a factor of 2, and we can leave ourselves with the equation of x plus y equals 180. Okay? And we know that if that's the case, these two angle measurements, therefore, are supplements. Okay? These are going to be supplementary angles because they add up to 180 degrees. So if we look here at these consecutive interior angles, okay, if I were to extend these lines again, okay, and looked at AB as my transversal, we have consecutive interior angles. Okay, when we have two lines cut by a transversal, we have consecutive interior angles that are supplementary, and that is one of our parallel lines theorems. So by the converse of the consecutive interior angle theorem, okay, then that means that BC is parallel to AD. Okay, so that's one side. And then clearly because you have these two right here, you can prove BC is parallel to AB, but you can grab another pair and do the exact same thing. Okay, so similarly, all right, this also proves that AB is parallel to CB. Okay, so again, with these proofs, once you find one, the second one is actually kind of the same. All right, I actually kind of forgot to mention the one above here. Right, we actually only technically proved that AD was parallel to BC, but you could see pretty quickly, I should have included this, right, that if we picked another pair of angles, say like here, call this like 3 and 4, I can do the same thing with 3 and 4 being congruent by CPCTC, and then they are alternate interior angles with AB and CD. So similarly, AB is parallel to CD. Okay, so the proofs are more here for your just general understanding. Essentially, all of the properties we talked about the other day, their converse can be used to prove that a quadrilateral is a parallelogram. So we have a few more, okay, a couple more. One of the properties the other day was that in a parallelogram, or actually in a parallelogram, we know that the opposite sides are congruent. We know that the opposite sides are parallel. So this theorem uses a little bit of both here. Okay, so this is an interesting one where if in a quadrilateral, so if a quadrilateral has one pair of opposite sides that are both parallel and congruent, it is a parallelogram. Okay. So this proof we're actually going to use a previous theorem as well. So I'm going to do kind of the same trick as before, where I'm just going to draw in a diagonal. So we know this diagonal is congruent to itself by the reflexive property. And because in this case we're being given this one pair of parallel sides, I want to draw in this diagonal because now I have that pair of congruent angles. Okay, because these are alternate interior angles. So angle BCA is congruent to angle DAC by the alternate interior angle theorem. Okay. We also have, again, that reflexive property. AC is congruent to itself. And so we actually have congruent triangles here. So triangle BCA is congruent to triangle DAC by side angle side congruence. All right. So now that we have these congruent triangles, we can see that AB is actually congruent to CD by the CBCTC. All right. And now that we're here, we've now put ourselves in the situation that we had on the previous page where we have pairs of opposite sides that are both congruent. So I have a pair of congruent sides here, a pair here. Okay. So then the rest, we just use that theorem that we have already proven from 8.7, the fact that you have two pairs of opposite congruent sides. All right. Here we have the last one. All right. In a parallelogram, the diagonals bisect each other, and it so happens that the converse can be used to prove that it is a parallelogram. So if in a quadrilateral, the diagonals bisect each other, it is a parallelogram. Okay. So for this, I'm going to do a couple things. I'm going to actually label this middle point here E. Oh, sorry, a little off screen there. So I'm going to label that little point E in the middle. All right. And I'm going to kind of run through kind of a flow chart of a proof. We have angle BEC is congruent to angle AED. And we also have that angle BEA is congruent to angle CED. So these are both vertical angles. So these are both by the vertical angle congruence theorem. By vertical angle. Okay, so that gives us these. I'm not gonna mark them because it's gonna get a little crowded in here, but that gives you these pair of vertical angles that are congruent, this pair that are congruent, and now this gives us an information to prove that we have two pairs of congruent triangles now. So triangle BEC is congruent to triangle DEA. Be careful with the order. And we have the triangle BEA is congruent to triangle DEC, and these are both by side angle side. Okay. And now with these two pairs of congruent triangles, okay, BA is congruent to DC. Oh, I'm on the wrong side here, BC, so let me do this one on this side. BC is congruent to DA, and AB is congruent to CD, and these are both by CPCTC. All right, and now what I have is I have this pair of opposite sides that are congruent, this pair of opposite sides that are congruent. We just kind of piece those together and we use that theorem again, 8.7. You have two pairs of opposite sides that are congruent. Ends up being a parallelogram. Okay, so those are all the theorems. They're essentially all just converses of the properties from the previous day. This is really the only kind of new one. Pieces a couple of parts together. All right, so I'll do one proof with you, and then the rest of this will be your assignment for the second half of this week. All right. So we're going to do a full two-column proof for this. So I'm going to have I need my statements. I have my reasons. Okay. Given that this is a regular hexagon, so our given here, okay, is that JKLMNO is a regular hexagon. And that is given. Okay? So what does it mean for it to be a regular hexagon? So regular is both equiangular and equilateral. So it is equilateral. So we have all these sides that are congruent. Okay? So I'm going to write those down. So I have JK is congruent to KL, is congruent to LM, MN, NO, and then OJ. Okay? So we have all of those, and all of the angles are congruent as well, but I'm actually only going to write down two of them. I'm only going to use two. Angle J is also congruent to angle M. So I'll mark those here. So those are not the only pair of congruent angles in this diagram, but I don't want to write down a bunch of extra stuff that I don't need. And I don't want to draw in all the other angles too, because angle N in this case is really the combination of two different angles, and I don't want it to get confusing. Okay. So these, okay, this is all the definition of regular polygon. Okay, regular polygons are both equilateral and equiangular. So now you want to think about what I need to be able to prove here. So I have in this quadrilateral, right, which is what I'm trying to prove this quadrilateral is a parallelogram. I already have one pair of sides being congruent, so I either need to find the other pair of sides being congruent, or I need to actually do a ton of extra work and get a bunch of parallel stuff. Now the parallel things might be doable, okay, but it looks like the just opposite sides being congruent might be the easiest path to go here, especially now when I look at these two triangles. Okay, I'm going to prove that these triangles are congruent now by side angle side. So you have these sides that are all the same. They have these included angles that are the same. So let's do that. So triangle OJK is congruent to triangle LMN. And this is the side angle side. And that will allow me now to say that OK is congruent to LN. And that is CPCTC. So this is a different measurement, but those are equal to each other. All right. Now, as much as I want you to know the reasons why you're able to prove things to be a parallelogram, I don't really care about you memorizing the numbers. Okay, so we've proven now that OKLN is a parallelogram. All right, and I definitely don't want you to memorize things to the extent where you're saying that this is theorem 8.7. It's totally fine for you to say that this is a parallelogram because it is a quadrilateral with two pairs of opposite congruent sides. Okay, so if you just say that, that's perfect. You don't really have to. Please don't call it 8.7. We don't have time to memorize every number in the book. Okay. All right, so there's a large variety of practice questions on here. So instead of giving you book work, I'm just going to have you work on this stuff. I hope you guys stay well. Email me if you have any questions. Come see office hours. And I hope you and your family stay safe. Take care.